G'day chemistry students. In this video we're looking at dot point 5, point 4, point 3 and 5. The focus of the video is to be looking at how the size of Ksp can give us information about what equilibrium systems are doing. So we're going to be looking at how temperature changes up K values just like they do for any equilibrium, but we'll look at it from a solubility perspective. We're also going to be focusing on Ksp and solubility. So the idea that the size of the Ksp value will dictate how soluble a substance is. And then we'll also be looking at comparing K and Q values to predict whether or not precipitates will form. Let's get into it. So first off, we can be looking at Ksp and temperature. Very similarly to the stuff outlined a couple of weeks ago, Le Chatelier's principle says that an equilibrium system that undergoes a temperature change will make an adjustment to counteract the change. And that will cause a difference in product and reactant amounts. As such, that will have an impact on Ksp. So depending on whether or not the forward or reverse process is exothermic or endothermic, you're going to end up with different concentrations of your ions at the end for our solubility product, which means that at different temperatures, the solubility of a substance is going to be different as well because the concentrations will have changed. This can be visually expressed using solubility curves, something that we will look at from time to time. What we should notice is that for all of these substances listed, and pretty much any ionic substance just in general, the solubility of the substance will change as temperature changes. As a result, in turn, that will mean that the Ksp value will also be adjusted. When we're looking at Ksp, the size of the value can give us an inkling as to how soluble the substance will be. We already know that Ksp is a product of the anion and cation concentration. If there's a low concentration of products that we end up having when multiplying two small numbers together, that's going to mean that we have a really low Ksp value. So what you'll see is Ksp values that are low. That will generally mean that there is a low solubility for the substance. In contrast, though, if we have high concentrations of products, meaning that there is a high solubility, a high threshold before we get to a point of saturation, and that will mean that our Ksp value will be high as well. Two large numbers multiplied by each other leads to a larger number in turn. Using some of those concepts, that can also help us to come up with a Ksp versus Qsp style of problem solving. So Ksp is our solubility product. It's the product of the cation and anion concentrations at equilibrium. In other words, the point of saturation where no more ions can be formed, no more dissociation can happen in the solution. These values are always constant, similar to KEQ. They're experimentally determined at different set temperatures. So the substances that you see on the data sheet all have really low Ksp values. What that means is that they have low or little solubility, and those substances can be found on your HSC data sheet. We also know that the Ksp of different salts can change depending on the salt itself and what its solubility is, but it can also change due to temperature. In contrast, we have our ionic product, our Qsp. And this is going to be the concentrations of anions and cations that are put into the equation, but that could be at any point. It could be at the point of saturation, but it could also be a point where the salt is undersaturated, meaning that more salt could dissolve, or it could be supersaturated where too much salt has dissolved and there's going to be precipitate that comes out as a result. So essentially meaning a left shift or a right shift if you're looking at it from an equilibrium standpoint. And the value of the solubility product will then also have an impact on what type of salt we're looking at, and will also be impacted by the temperature as well. What we can use Q for is to determine whether or not a system has reached that point of saturation, that point of equilibrium. In other words, if Q and K are the same, they are in equilibrium. However, if Q is lower than K, what we can assume is that the cation and anion concentrations aren't large enough, we're still approaching equilibrium, and that no precipitate will form. And if Q is bigger than K, what we can expect is that the cation and anion concentrations are larger than they should be, meaning that we have a supersaturated solution. When we're doing a Ksp versus Qsp calculation, very similar to our K versus Q that we did a couple of weeks ago, what we need to do first, like for most of these calculations is first identify what the balanced chemical equation is and come up with an equilibrium expression, our ionic product. What we then need to do is find the measured concentrations for the particular scenario that we're looking at and substitute them in to calculate the Q value. We can then do a comparison, and depending on the size of Q, we can then predict whether or not there will be a precipitate formed or where the equilibrium system needs to proceed. I have a practice question prepared, so let's get into that. All right, in this video's question, what we're being asked to do is look at a solution of barium hydroxide. Now, 0.5 grams of the salt was placed into 200 mils of water at 25 degrees Celsius. It was then stirred. The question is, we need to figure out whether or not a precipitate will form given that the Ksp for barium hydroxide is 2.55 times 10 to the negative 4. So in this question, what we need to be doing is figuring out what the theoretical concentration is for the solution, then determining Qsp, our ionic product, and comparing it to Ksp to determine whether or not we have exceeded our threshold of solubility. As with all questions, the first thing that we need to do is identify the balanced chemical equation. So we're looking at barium hydroxide in this case. And again, as always, because we're looking at a solubility kind of question, we're looking at the dissociation of barium hydroxide. So that's going to end up forming barium ions and hydroxide ions. And that's aqueous. And this guy's solid. Second step that we need to do is write up an equilibrium expression. So that's using the information up above to form our solubility product. Ksp is equal to concentration of barium ions times the concentration of hydroxide ions. Because of our ratios, the hydroxide ion concentration is going to be squared. Next thing that we need to do is to determine, based on the information that we've been given, what the concentrations of the ions will be. And that's going to be based on this first set of information that we have at the top of the question. So we're going to be able to figure out what the concentration of the barium hydroxide is, and then from there find the ion concentrations so that we can substitute them back in to our Q value. Speaking of, I just noticed that of course we are calculating not Ksp, but Qsp instead. We've been given the Ksp value, and that's what we're comparing it to. So my mistake, but anyway, there's your correction. First thing that we need to do is figure out the concentration of barium hydroxide. Now, given the information that we have, we know that it is equal to 0.500 grams per 200 mil of water. That's not a great value to be working with. Let's get this in a per litre value first. If I multiply this and this both by 5, I'll end up getting the concentration per litre. So 2.500 grams. Should probably just be 10. I'll carry 3 significant figures there per litre of solution. Next thing that we need to do is find the molarity. So to do that, we need to know how many moles this mass is. So N is equal to M over MM, which is equal to 2.50 divided by the molar mass. Again, you can just find that by adding up all the substances from the periodic table and looking at their molecular masses. So 171.3, I should say, is our number there. Put that into a calculator. That's going to be equal to 1.46 times 10 to the negative 2 moles per liter. So that is the number of moles present in a liter of solution. So I've not just written that as moles, but just written that as a concentration straight away. That will just flesh out the working a little bit more. What we can then say automatically is that this is also the concentration of barium ions. And we know this because the concentration of barium ions is equal to the concentration of our barium hydroxide ion, which we just calculated. That's got to do with the 1-to-1 ratio in the empirical formula. And that's due to the fact that there is one barium for every barium hydroxide unit. And that also means then that the concentration of the hydroxide ion is equal to 2 times the concentration of the barium hydroxide due to our empirical formula, the ratios that exist there. That is 2 times 1.46 times 10 to the negative 2 moles per liter, which is 2.92 times 10 to the negative 2 moles per liter. So both of these values are super important, very much necessary, because what we can do is take those values and substitute them into our QSP equation, and that is step number 4 up the top. This one here, substitute concentration to calculate QSP. So QSP is equal to our barium concentration times our hydroxide concentration. Noting as well that we've got to square that value, so I've done that as well. Put that into a calculator. That should give us 1.24 times 10 to the negative 5. Now, if this is the case, our last step, the last thing that we need to do, step number 5, compare QSP and KSP. So I'm going to be doing that now. Now, we've been told that KSP up the top is equal to 2.55 times 10 to the negative 4. So we've got QSP. I'll also write KSP. 2.55 times 10 to the negative 4. This means that QSP is less than our KSP. And if this is the case, then the concentration of ions is below saturation point. If this is the case, then that means that more ions can be dissolved, therefore there will be no precipitate formed. And there we go, we've been able to make a prediction on the outcome of the formation of a solution, whether or not it will form precipitate, using our KSP versus QSP concept. Thank you very much, everyone. In the next video, what we're going to be doing is looking at outlining a method that we're going to be conducting in class to experimentally determine solubility and start forming a solubility curve. But until then, have a good one.